or sequence of packets to the server. This is the guess. If the guess is incorrect, those bits turn into basically random instructions, and the server should crash. If the guess is correct, the server should do something that the remote attacker can observe, and the attacker learns those bits of the key. OK, so in order for this type of attack to work, we need some properties of the server. We definitely need a vulnerability. We need some way of injecting our guess into the server. Luckily, most servers are vulnerable, so this isn't too much of a problem. Any old buffer overflow will do. If we didn't have vulnerabilities in servers, we wouldn't have to worry about any of these techniques at all. Since we need to make lots of guesses, we also need some way of making repeated guesses without the randomization key changing. So that means we can crash the server without the server being re-randomized. So some implementations would re-randomize the server every time you load it. As long as the server forks processes, we can still do this. So if it forks on request, like Apache does, we can crash one of those fork processes, but the other children and the parent are still running with the same key. So the third property we need is it has to be observable. We need to be able to observe, as a remote attacker, whether or not we crash the server. And the final property is it needs to be easy to cryptanalyze the key that's used for the randomization. We're doing all this work to learn one plaintext ciphertext pair. That has to be enough for us to figure out the key, because if we want to inject code into the process, we need to know what the key is. Luckily, with XOR, this is really easy. OK, so we need to have some idea of a short chunk of code we can put in the process and tell whether that guess is correct. The shortest thing we could do is a 1-byte instruction. And we probably need a control instruction. Otherwise, we can't tell what's going on. But if we inject a return instruction, well, if the guess is correct, the process returns. And that should be noticeable. If the guess is incorrect, the process should crash. The problem with the return attack is even if the guess is correct, the process is likely to crash soon anyway, because it leaves the stack in an inconsistent state. So this only works on vulnerabilities where the server does something that we can observe remotely before it crashes. So what I'm going to focus on today is the jump attack, which works on almost all vulnerabilities. So the jump attack is to try to guess this phoebe instruction, which is a jump with offset -2. When we put that on the stack the right way, it looks like phoebe backwards. And that means we need to guess 2 bytes at once. So there are 2 to the 16 possible guesses, which seems reasonable to brute force. And we'll notice if we're correct, because when we jump to offset -2, we're jumping back to the same instruction we just executed. So that means it's going to produce an infinite loop. The socket's going to stay open. So when the server crashes because the guess is wrong, the socket gets closed. The remote attacker can notice that. When we have the infinite loop, the socket stays open, and we can tell that we guessed correctly. OK, so here's what this looks like. So we've got a vulnerable buffer on the stack. We've overridden return address to jump to some location. And we've tried to guess at that location the jump -2 instruction. If we guess correctly, we get an infinite loop. So once we've found one correct guess, right, we need more bytes because each byte has its own encryption key. Well, we can move up to the next byte. And if we move up 1 byte at a time to guess the next one, well, we can do that at 1 byte at a time. So we only need up to 256 attempts. Right, we can use the ones we've already guessed to put known things there. So we can put the -2 offset in the right place and guess the remaining bytes much more quickly. OK, so there are 4 things that might happen. Right? This is a simple case where if we always guess correctly, we get the infinite loop and we observe that. And if we guess incorrectly, the server crashes. It'd be great if that was true. Right? We know right away when we have the right guess. Unfortunately, it's not that simple. We can guess something that's incorrect, and the server goes into an infinite loop anyway. That would be a false positive. We could guess something that's correct, and the server crashes anyway. This shouldn't happen too often. Right? This would only happen if there's something else that causes the server to crash that time. So we don't have to worry about that case. And we could guess something that's incorrect and causes the server to crash, and we observe that, and we make progress because we know that's not correct. the case we have to worry about is this false positive case, where we guess something that's not correct, but the server behaves like we made a correct guess, that it goes into what looks like an infinite loop anyway. So there are lots of things that could cause this, right? If we did, instead of guessing a jump -2, the bytes we happen to inject decrypted to jump -4, and whatever instruction happened to be at the -4 location was a harmless 2-byte instruction, then we would still get an infinite loop, but we wouldn't know the correct mask. We could also guess something like a jump non-zero, and if the state of the processor is such that that condition would be satisfied, then that would behave just like an infinite loop as well. So the other kinds of things that could cause the behavior to look like an infinite loop, even though we didn't guess correctly, well, we could just guess something that's harmless. And by harmless, I mean any guess that doesn't cause the processor to crash right away. It could change the state of the processor, but it doesn't cause it to crash. And then some subsequently executed instruction could produce an infinite loop. The third case is probably not too serious. We could make the incorrect guess, and it could cause the server to crash. But because of network lag or because of load on the server, it doesn't crash quickly enough. And then the client of the attacker would think, well, it's an infinite loop. You have some amount of time you can wait to decide if it's an infinite loop or not. And if you exceed that time, even though the server crashed, but you didn't crash in time, then you would infer that's an incorrect guess as well. We can sort of solve this problem by just increasing the timeout that we're willing to wait. That slows down the attack, though. OK. So the good news is we can distinguish those cases, right? So if we have multiple guesses at some location that all produce infinite loops, we can try injecting different instructions there. And guessing the different masks that produced an infinite loop before, we encrypt some other instruction with that mask, and we see what we get. And if we put the no-op in, if the mask is correct, that will do nothing, and it will go on to the next instruction, which produces the infinite loop, because we can put our known infinite loop instructions there. So this will allow us to distinguish some of the incorrect guesses. It doesn't always work. So there's a difficulty that the instruction set is very dense. And if two of the guesses differ in only 1 bit, there's no harmless instruction that is always harmless for changing 1 bit and always harmful if we have the other version of that bit. So we can't always distinguish here. But with enough different harmless instructions and some other tricks, we can distinguish them. Turns out that there's actually even better news about the false positives. Right? What causes them is not random. Right? The false positives are caused because of the structure of the instruction set. So we know that when we've hit a false positive, we're running into one of these things that can cause it, which is most likely a conditional loop. And the instruction set very conveniently organizes where the conditional jump instructions are, that they all start with the same 4 bits. So all the opcodes that start with 7 are conditional jumps. And they come in complementary pairs. And what that means is if the last bit is a 0 and the jump would not be taken, then the complementary instruction with the last bit of a 1 would always be taken. So you can think of one of these would be jump if 0, one of them is jump is non-zero. And all 16 of the conditional jump instructions have this property. That if we flip the last bit, one of those 2 is guaranteed to be taken. So this means with just 32 guesses, we can always find at least one infinite loop. Because all we have to do is guess all possible values for the first 4 bits to try to find the 7, and guess both possible values for the last bit. And so we only need to try 5 different bits. The other 3 bits can be anything. We don't care what they are. We don't need to make guesses there. So we only need 32 guesses to find an infinite loop. Once we find one, we don't know which one we found. So we need some extra guesses to distinguish which mask is actually at that location. And that requires about 8 additional guesses. So here's what this looks like now. So once we've learned a few locations the hard way, what we can do is place a near jump there with an offset, which is the original return location. So this has a nice property that we're not creating any more infinite loops. Right? And infinite loops are a problem.